Everyone. I hope I'm audible. Okay. Okay. So today we'll start with some problems related to critical point theory, and then we'll discuss the definition of manifold, the three equivalent definitions, and some examples related to it. Okay. So let's start with first question number one. So that a critical point critical point A is a saddle point if and only if for any ball around A, there are points X and Y in the ball such that Fx strictly less than Fa strictly less than F. Let's recall what do we mean by a saddle point. Saddle point is basically a critical point which is neither maximum nor minimum. So let's recall. That a critical point that is not an extrema extrema is called a saddle point. So we know that we have two kinds of extremas. Extrema, we have minima and maximum. For the case of minima, we can suppose we are talking about local. So a local minima, for a local minima, we can find a ball. There exists some ball R positive such that F, suppose this is x naught, such that Fx naught, this is less than equal to Fx for every x lying in this ball around x naught. Similarly, for local maxima, we can find a ball such that this Fx naught, this is greater than equal to Fx for every x in this ball. Okay, so using this definition, we'll see that of course, it might be clear enough that if a point is neither maximum nor minima, then it is a saddle point, and in that case, uh, neither of these inequality will hold, or we can say that both of them will hold simultaneously. So let's formally prove this. So yeah, this is an if and only if type of statement. We'll start with one side. Let's start with A being the a saddle point. let A be a saddle point. Saddle point of F. This implies clearly F is a critical point. F dash A is equal to 0. Now, we want to show that there exists some X and Y in any ball. In any ball around A, let R positive be arbitrary. In any ball, we can find such X and Y such that Fx strictly less than Fa, strictly less than F. Suppose this does not hold. Suppose our claim is false. This implies there exists some R not positive such that either of these inequalities will not hold, such that either Fx will be less than equal to Fa for every Xa in BA naught, or Fx will be greater than equal to Fa for every X in BA naught. Now this first statement will give us that the point A is actually a local minima, maxima, because we are able to find some ball where all the values at each point X in this ball, the value is lesser than or equal to Fa. So that means this A is a local minima. Now this will give us that A is a local minimum. And in this case, we'll get that A is a, sorry, this is maximum. And in this case, we'll get that A is a local minimum, which is a contradiction because our A was a saddle point. Now this gives us a contradiction. This will also give us a contradiction because A is a saddle point. Since A was a saddle point, we will get a contradiction. Hence, there exists some X and Y in BR should write it this way. BRA such that Fx less than Fa less than. So I hope this one side of the proof was clear. We started with the fact that suppose this statement does not, we started with the fact that A is a saddle point and we wanted to show that such an inequality holds. That means there exists some X and Y in every ball. In every ball, we can find such X and Y. So we started with the assuming that suppose this does not hold. That means in some neighborhood of A, either of the inequality will not hold, or we can say that one-sided will only hold. So yeah, in that case, we can find some real number are not positive such that and the ball B are not A, either will get less than equal to or greater than equal to everywhere. And in both the cases, we'll get contradiction because our point is a saddle point. Okay, so this was clear enough. Conversely, we'll see that then also if a critical point satisfies this condition, then clearly it is neither maxima nor minima, hence a saddle point. Conversely, suppose f dash A is 0 and for any for every r positive, there exist points xy such that fx less than xy in BRC A, fx strictly less than fa strictly less than f. Next, we in this case, we'll show that f is a saddle point. Sorry, A is a saddle point. Clearly, if it is not, and since it is a critical point, then it will be either maxima or minima, local maxima or minima. Suppose not, then since A is a critical point, this implies either A is a local minima or A is a local maxima. Now this will imply that there exist some R naught positive such that fx is greater than equal to fa for every x in BR naught A, and this will give us there exists some R naught positive such that fx is less than equal to fa for every x in BR naught A. But according to the given condition, since this R naught is some real number, there must exist some y in BR naught A such that fy will be strictly less than fa less than equal to fx, which will give us a contradiction. Similarly, in this case, we will get a contradiction. Hence, A is a saddle point. A is a saddle point. Yes, you wanted to say something? It was showing typing. You can does derivative at a given point to be 0 in converse part? Yes, that was I think that should have been added in the problem itself. A critical point is a saddle point if and only if this condition holds. So we started with a critical point A. So A is a critical point. Then we say that it is a saddle point if and only if such condition holds. I don't think without critical point we can say, because for converse part, if we take the function fx is equal to x, suppose, in that case also any point, this A, whatever neighborhood I take, whatever small neighborhood I take, I'll be able to find 2 points, x here, y here, such that fx strictly less than fa strictly less than fy. That would give us that every point is a saddle point. But I don't think that's correct. So yeah, therefore we should take this A to be critical point, then say a critical point is a saddle point if and only if such condition holds.
Okay, ma'am.
Therefore, this A is a saddle. Okay, I hope this proof was clear. This was nothing, just I wanted to explain you how we should write. So since we are proving some if and only if type of statement, we should start with one side and claim that the second one is true. And in order to show that the second one is true, I started with kind of contradiction. Suppose this does not hold, and ended up getting some contradiction. So this is how we write. This is all about mathematics as a language.
Ma'am,
Hmm?
when gradient is zero, then derivative will also be zero. Uh,
Yeah. If you remember, we have a definition of derivative in terms of the gradient. The derivative in case of finite dimensional spaces, it is a linear operator. Linear operator eventually that will be some matrix, and that was actually given by this vector. I'll explain. Suppose,
that will become zero matrix.
yeah, zero matrix in the case of gradient being zero.
Yes.
Mm-hmm. Next, we'll look at some quadratic
Does
form.
converse will true if
What
derivative
kind?
zero, then does gradient will also be zero?
If the then all the partial derivatives will also be zero, no? Partial derivatives being zero means the gradient will be zero.
Mm,
If you remember, we had a definition something like this: f of a plus th minus f of a upon, I don't remember, something like this. If the if the function is differentiable, then it goes to zero. The derivative is zero.
norm of f a plus th minus
Yeah,
f
yeah,
a
yeah.
minus. Oh, yes, yes, yes.
So if the function, the derivative is zero, that will eventually give us that all the partial derivatives will be zero. And for the finite dimensional case, if our function f is, if our function is something from Rn to R, in that case, if all the partial derivatives are zero, so eventually dfx, this will be a linear map from Rn to R, and this linear map is nothing but
One cross
this,
n matrix.
yeah, 1 cross n matrix, and the components are just the partial derivatives.
Mm,
So yeah, in that case, the gradient, that's basically the gradient vector, no? So this will be
yes.
eventually gradient vector at point x. So yeah, gradient will affect the derivative.
So this is the if and only if condition.
Yeah, in case of function from Rn to R, you can say that this is if and only if. Otherwise, I don't know, because otherwise it will be a matrix.
Mm.
In that case, I don't know. But in this case,
Gradient function is defined on a real valued function or
yeah, otherwise we don't have the concept of gradient, no?
oh, oh, okay, okay.
Mm-hmm.
Okay, ma'am, thank you.
Okay. Next, we'll look at some quadratic forms. We say that a quadratic form is semi-definite. Quadratic form
When
will
eigen values are greater than equal to 0, I think.
hmm, but that is a consequence of the definition. So the exact definition should be semi-definite if either this qx is greater than equal to 0 or qx is less than equal to 0. So those eigenvalues are of the matrix corresponding to which the quadratic form is formed. So the quadratic form is something of the form x transpose ax. The eigenvalues you are talking about are the eigenvalues of this matrix.
Yes.
So yeah, when talking about the quadratic form, so eventually that will lead us to the same thing. The only difference is that we need to remember is that for semi-definite case, we have qx greater than equal to 0. Suppose we are talking about positive semi-definite. And for positive definite, we have qx strictly positive for every x non-zero, and qx can be 0 only for x equals to 0. For semi-definite, it can be 0 for other points as well, but for definite, for positive definite, it should be 0 only at 0. Okay. We say that a quadratic form is semi-definite, yeah, positive or negative, if either qx greater than equal to 0, less than equal to 0 for all points. Consider the three functions f1 xy. This is x squared plus y power 4. f2 xy is just it's negative minus x squared minus y to the power 4. And f3 xy, this is equal to x squared plus y cube. Will determine the nature of critical point 0. So yeah, you can clearly see that 0, 0, 0 will be critical point of all these functions. Determine the nature of the critical point. That means we need to see whether this is a point of maxima, minima, or a saddle point. And critical determine the nature of the critical point 0, 0. Further, also compute the quadratic form associated. Also compute the quadratic form associated to the Hessian of each of the functions. So we'll start with the uh, nature of the critical point. So yeah, f1 xy. This is a function from R2 to R. You can see that a point will be a critical point of this function if and only if. So x naught, y naught is a critical point of any function f from R2 to R if and only if the partial derivatives, all the partial derivatives are 0 at that point. That means del by del x of f at x naught, y naught is equal to 0, and simultaneously del by del y f at x naught comma y naught, this is equal to 0. So you can see that here The partial derivatives will be 0 only at the origin. Clearly, 0, 0 is a critical point of F1. Next, we'll see whether this will be maximum minima. Clearly, you can see that x square and y power 4 will always be positive. So in that case, F1 xy x square plus y power 4, this is always greater than equal to 0. And 0 is the value of function at point
0, 0.
origin. 0, 0. That means the point origin is global minimum.
Local minima.
Global, it will be eventually global because it is happening for every x, y, and
Mm.
so this implies 0, 0 is a the global minimum. Similarly, you can see the function f2. It's just the negative of f1. Similarly, f2xy, this is minus x square minus y power 4. Again, 0, 0 will be its critical point. Clearly, origin is a critical point of f2 and f2xy. This will be always negative, which is the value of function at 0, 0. This is happening for every x, y, and r. Therefore, the point origin turns out to be the global maximum.
Here we
Global.
have to check that 0 is value of that function at some point.
Yeah, in
If
that
you,
in this case, it was very easy to see now because f at
Mhm.
0, 0 will be 0. And since we had even powers, x square, y power 4, so we were easily able to find the relation between the function values and 0.
Mm,
In next case, yes,
if 0 is not a value of any point, or then we cannot
then
say that
that
it
would,
is
no, no, no. In
okay.
that case, we cannot directly say. In this case, it was clear enough, so we were able to see.
Yes.
Yeah. In next function, you'll see that we have power 3 as well. So in that case, it will be a bit tricky. So we have x square plus y power 3. In this case, we cannot directly say that the values will be always positive or always negative. So try to see clearly. I hope you can see that origin will again be a critical point of this function. Clearly, again the partial derivatives will be 0 only at origin. 0, 0 is a critical point of f3. Now f3 at the value of the function at this critical point, it is 0. We need to see what happens in the neighborhood of origin. So in the neighborhood of 0, 0, whether the function, the values are greater than the value at f0, 0 or the less than the value at 0, 0. So basically you need to see whether
It will be saddle point.
hmm, so you'll have to show how this is
Mm,
greater than f300 or
if we go through y-axis,
okay. Through
so
y-axis, that means
0 and k, f0 y will be yq, and when we tend y to be 0, it will
okay.
be
So you're
positive or
saying
it will be
so you're saying if we take x equals to 0,
yes.
Can you please repeat? You're saying if we take x equals to 0,
And then f0y will be y cube.
0y will be y cubed.
And when y tends to 0, so
Okay.
then
Limit y tending to 0. Or you're talking about neighborhood.
yes, yes, neighborhood of in every neighborhood of 0, we will find y, which will be
We
positive as
can
well
find.
as negative.
So basically,
So
in any neighborhood, in any neighborhood of
0, 0.
0, 0, we can clearly find points of this form. We can
Yes.
find y in, or instead, we can find points 0, comma y1 and 0, comma y2 such that y1 is positive and y2 is negative. In that
Yes.
case, we have f at 0, comma y1, this will be equal to y1 cube, and since y1 is positive, its cube will be positive. Whereas if y2 will be y2 cube, and since y2 is negative, its cube will be negative. This
Mm.
is f3 at 0, 0. This is f3 at 0, 0. Therefore, in any neighborhood, we are able to find two distinct points where the values are greater than as well as or and less than. So by previous problem, we get that this point is a saddle point.
Mm.
Okay,
Yes.
are able to find points x naught and y naught in any neighborhood. Now, since this existence of these points is independent of the neighborhood, whatever small neighborhood of origin you take, you will obviously able to you will be always able to find y1, y2 such that one is positive and the other one is negative. Any neighborhood origin
Then this point
such
cannot
that
be either local minimum nor local maximum.
therefore by previous problem we can say that since a was a critical point or origin is a critical point such that we are able to find such points, therefore it is a saddle point. So that similarly you can take the path. So what I did was we can take walk along y equals to minus 2 x to the power 2 by 3. In that case, if x comma minus 2 x to the power 2 by 3, that will give us x square minus 8x square. So that's minus 7x square, always negative. And along the path y equals to 2x to the power 2 by 3, in that case, if 3x, 2x to the power 2 by 3, this will become 9x square, which will be always positive. So basically, whenever we take some ball around origin, so minus 2x cube will be some function of this form, and 2x, yeah, 2x to the power 2 by 3 will be function something of this form. So whatever small neighborhood you take, you can find points lying on these paths, and eventually on the different path, you are able to get greater than and less than. Yeah, similar kind of approach. Okay. So yeah, good. So in this case, the critical point 0, 0 turns out to be saddle point. Next, we need to find the compute the quadratic form associated to the Hessian of each of the function. So, do you remember how we evaluate Hessian of a function?
We evaluate the second order partial derivative and put it in the matrix form.
Matrix form. If our function f is from R2 to R, suppose, in that case, Hessian of f, this is, and it should be, yeah, of course,
Del
C2
square f
is,
by
yeah, del 2f by del x1 square. So yeah, the a11 component is actually partial derivative with respect to first variable two times. Then we have a12. So with respect to second, with respect to first, to f x two del x1, so this will be 1 2, and del to f x2 square. So yeah, in first case, our function f1 xy, this is x square plus y power 4. So tell me what will be the Hessian of this function.
this will be 2 0 and 0 for y square. Sorry, 12y square.
Well, and then we need to find the quadratic form corresponding to the Hessian. So if I treat this as A1, now we need to find the quadratic form. So that will be Q from R2 to R, Q at point XY. This is just matrix multiplication XY, A1, XY. So yeah, tell me what will be this. This is Q.
Ma'am, this xy and the xy in A1, both are
Same,
same or different?
same, both are same. Both are treated as variables.
This will be 2x square plus 12y4, I think.
2x square plus 12y power 4. So what can you say about this quadratic form? Is it positive definite, positive semi-definite, negative definite, or negative semi-definite?
A positive semi-definite greater than equal to 0 for all xy.
And where is it zero?
At origin,
It is zero only at origin. Otherwise, it
yes.
can't be zero. So therefore, it is positive definite because it is zero only at the origin. For any point other than origin, it is strictly positive.
Oh, oh,
So this is strictly positive for every xy not origin, and this is
for
equal to 0.
semi-definite, we have
It can be 0 at other points as well. But when it is non-zero for in every non-zero point, that means it is positive definite
yes.
or xy equals to 0 0. Therefore, this q1 is positive definite. And you must have read this, that if the quadratic form corresponding to Hessian at a critical point is positive definite, in that case the critical point is actually a global, or I think it's local minimum. In this case, it is turning out to be global minimum.
Minimum.
Similarly, let's do this for function f2.
Local minima and global minima also. Yes.
In this case, we are getting it to be global minima, na?
Yes, ma'am.
F2 xy, and this is minus x square minus y power 4. So what will be the Hessian? F2 This case just the negative. Get everything negative. Minus 2, 0, 0. Minus 12y square. And the corresponding quadratic form q2xy. If I mark this, take this as e2, this is xy e2 xy. So this will be
Minus 2x square minus 12y4
minus 2x square minus 12y by 4. And in this case, the quadratic form is
is negative definite.
negative definite. Q2 is negative definite, and hence the critical point is
0, 0. It's a local
maximum.
maximum is
Hmm, negative definite. For the case of function f3, so this is x square plus y cube. In this case, your Hessian will be, yeah, this time it will be a bit different.
2006y.
Hmm, 6y. If I mark this as A3, then we have Q3 xy xy A3 xy. This will be
2x square plus 6y cube.
6y cube. Now, can we say anything about this quadratic form Q3?
Um, So this will be, I think, saddle point.
Yeah, so it was saddle point in this case. So basically,
Mhm.
this quadratic form is indefinite because it can take positive, negative, as well as zero values. So
With
this
points other than 0. Okay.
this Q3 is indefinite, and we know that in the case of indefinite, the critical point, we cannot say anything about the critical point, and in this case also it was neither maximum nor minimum. Definite was a saddle point. Saddle point also we were able to see in this case. The function was very kind of easy to understand. Many times it happens that you can't analyze what is happening, so the case of indefinite is not considered a good case. Okay. So yeah, I hope this question is fine. Hmm.
The exactly same question asked in assignment 8.
Okay.
The
Okay.
three functions are given. The first
Hmm.
function fxy is equal to x square plus y cube.
F of xy is x square exactly same.
No, in gxy is equal to x square plus y4.
Okay.
These both are same. And third one hxy is x square minus y4.
Yeah, in this case,
And in the first
you.
option, which says that the quadratic form obtained using the Hessian of these functions are
Hmm.
all x square. And this was right option given to be right.
The Hessian corresponding to these functions, in all, the Hessian corresponding to these three functions was
X square, all x square.
something like this.
No, only x square. It,
So the quadratic form, quadratic
yes, it's
form
quadratic
corresponding to
form obtained using the Hessian
Hessian,
of these functions are all x square.
but we are not getting that.
Hmm, only x was there.
So was
Where
that
is
asked
y?
at point on some on x-axis? So
No,
basically, I think they are taking y equals to 0.
Hmm. But it was not given.
So it was an assignment problem.
Yes, second
I'll
assignment.
okay, I'll check what's the
Week
issue.
8 assignment problem. Question number
Okay.
2.
Okay. So yeah, exactly same functions, no?
Yes. The third one is actually,
Yeah. But then also for first two we should have got the same thing, no?
yes.
Okay, I'll check that. What's the problem? Because I don't think we did something wrong. It was just basic definition. We applied the definition of the Hessian, then that of the quadratic form.
Quadratic form. When we check at 0.00, then it's fine.
Yeah,
Other
but
thing,
0, 0 is fine, but in none of the case we got x square.
yes.
Okay, I'll see what's the problem. Maybe there was something else in the question, something
Yes.
specific. Okay, I'll see that. Let's move to next question. Okay. Let A be a 2 cross 2 symmetric matrix. Two cross two matrix. Formulate a precise condition on the entries that allows us to determine the nature of the quadratic form associated to A. So since A is a symmetric 2 cross 2 matrix, we can write this matrix to be something A, B, C, C. Something of this form. This is a general symmetric matrix of order 2 cross 2, where A, B, C are some real numbers. Then let's look at the quadratic form associated to the matrix A. Maybe there we need to take the Hessian at the critical point. So here, if we take this Hessian F1 at 0, 0, this will be 2, 0, 0, 0. In that case, 1x will be x 2, 0, 0, x y,
2x
2x.
square.
In that case, also we are getting 2x square, not x square. No?
Hmm.
So is it written in the problem?
When I go to Chat GPT,
Hmm.
it says that in Taylor series expansion, the second part is 1 by 2 times.
Yeah, for Taylor
So,
series expansion, we basically multiply it by 1 by n factorial na, for nth term.
yes.
But that's multiplied by the Hessian.
Hmm. But I was confused how it will give the quadratic form x square.
And if we do similarly for the function f3, In that case also, again, because of this 2, we'll get 2x square.
Mm.
Here we see that. Okay, now the quadratic form corresponding to the symmetric matrix A, this is x, y, a, c, c, b, x, y. So this will be a polynomial in x and y. We will get this to be ax square plus 2bxy plus cy square. Now we want some condition over a, b, and c in order to get this quadratic form to be either positive definite or negative definite. So we can start with the case where this is always positive. So when can we get this q to be always positive? If this is something of the form, some square. So eventually,
Completing the square form, then I think.
yeah, all we need to apply is we need to see the conditions over a, b, and c. So if we take b such that this b is equal to root ac, suppose let's start with positive. Suppose all three of them are positive. A, B, C are positive, and we impose a condition. B is such that B is equal to under root AC. So in that case, this Q will be the square of root AX
Root
plus
x,
root.
y.
So no, this should be 2CXY. This will be BY square. So substance is equal to AB. Whole square. So in this case, this q will be positive definite, because yeah, it will be zero only if this x and y are both are zero. Similarly, you can see if suppose a b c and a b and c all three are negative, we can take that negative sign outside and then apply the condition over mod a b and c, and in that case we can make it to be negative definite. So yeah, look at that yourself. Check for
Uh,
other conditions.
What you said, man?
So suppose uh, these A, B, and C are negative. We can go for the next case, no? Next case
Hmm.
could be suppose A, B, and C are negative. In that
Then we can
case,
take
I can
minus sign
take
outside.
negative outside. So inside it will be mod
Positive.
AX square. Instead of minus A, I can write it to be mod A, no?
Oh,
And
yes.
then we can apply conditions on these mod A, mod B, mod C. 2 times mod CXY plus mod BY square. And similarly, as earlier, we can apply some conditions on mod A, mod B, mod C to get this to be negative. So
Hmm.
eventually, in that case, you'll get Q to be negative definite. Look at this precisely how the things will go here. Okay,
Hmm.
so let's move to a difficult task, the definition of manifold. I'll start with recalling the three equivalent
Manifold is
definitions.
very, very difficult.
Very difficult, even I was not able to get it clearly. So yeah, I hope with this discussion it will get better. Yes.
Hmm.
Let's start with manifolds. So we say that a non-empty subset of Rn, suppose M is a subset of Rn, M is non-empty, then we say that this M is a, we say that M is a d-dimensional CK manifold if either of the following equivalent conditions holds. So the first one, for any A in M, now M was just a subset of Rn, for any A in M, we can find an open set W. W is an open set in Rn such that it contains A. So it has nothing to do with M. It's just that A, an element of M, belongs to W, which is an open set in Rn. A belongs to W. Then we have another open set, an open set V in Rd, and a CK smooth function. CK smooth function, that means it is K times differentiable and its Kth derivative is continuous as well. And a CK smooth function F, which is defined on this V to Rn minus T, such that the set of points such that M intersection W. Now this M intersection W is a set of points in Rn, which should be the points x comma fx for every x in V. That means M intersection W gives the graph of f. So yeah,
And
clearly for hmm?
can we say M intersection W is open neighborhood of A as a subspace, uh, um, considering M
M,
as a subspace of Rn.
we don't know anything about M. M is just a subset.
M is subset of Rn,
Rn. It's just
and
a subset of Rn.
W is an open set of Rn.
Rn, yes.
So M intersection W will be open in M as a subspace,
We
isn't
don't
it?
know whether this M is a subspace or not.
Okay.
If it was a subspace, then that was the definition for open set corresponding to subspaces. No? Here we don't know
Mm-hmm.
anything about this M. M can be anything. In fact, these M, we will see that open balls will eventually form manifolds. Those open ball is never a subspace.
Ah,
Yeah, yeah. Open balls can never be a subspace, no? Because we cannot take alpha times x. Suppose this point x belongs to this set S, but alpha x will go outside, no?
so I'm saying metric subspace. I think in topological way.
Then also it should be a vector subspace firstly it should be vector subspace, then only we can talk about the subspaces. Huh? So I don't think.
Yes.
So yeah, right now please don't confuse it because we already have a lot of terms. So just
Yes,
assume that
sorry.
yeah, start with M being just a subset of Rn. Okay. Mhm. Yeah. If suppose we can find this F such that M intersection W is a subset of Rn. It is a graph of the function F. So graph of the function F is a set of points x comma fx. Now this x is in Fv, that V is x is in V is a subset of Rd. So this is basically D components. So x1, x2, and so on up to xd. And fx is an element in R, n minus d. So it has n minus d components, y1, y2 up to yn minus d. So eventually we are getting an n tuple. So yeah, this was the first definition. So in words, we can say that M, in this case, we can say that M is locally, yeah, because this W is just some, we can say that W is kind of a neighborhood of A. So we can say that M is locally a graph of some CK smooth function because, yeah, this F is defined on some open set, not on whole space R D. So in this case, in words, we can say that this M is locally a graph of a CK smooth function. Okay. So next we have another equivalent definition. Two, for each A in M, A in M,
And this X is from
X,
V
yes,
and V subset of RD. So,
yes.
so this X can from RD any coordinate can it be outside M intersection W?
It if M is a manifold, then we can find such function F and this sets V and W such that whenever we will take this X and V, this X comma Fx should be in M intersection W.
Oh, so it is definition. Okay, okay.
Yes, yes. So we are able to find such sets V, such open sets V, W and a function F, which is CK smooth. So yeah, this is CK smooth, such that this is happening. That's why we are saying that M is locally the graph of the function F. Basically, so in
Hmm.
some open set, it is giving us the graph of some CK smooth function. At each A in M, we can find an open set W in Rn with A belonging to W. Again, W is some other set. It is containing an element of the set M, and there exists a CK smooth smooth function such that, yeah, CK smooth map G is defined on this W to R n minus D such that M intersection W is the level set of G at 0. That means M intersection W, it is equal to set of all those points X in W such that Gx is equal to 0. Yeah, M is in Rn, so W is in Rn, X is in Rn. So basically M intersection W is kind of kernel of G, because it is level set of G at 0, set of all those points that are giving the value 0.
In level hypersurface set, gradient also should be zero, I think. Isn't it?
I think this is just, we are not talking about a hypersurface, it is just a level set. So in the
Oh,
definition of level set is just the set of points at which, yeah, I think it was derivative. Can you just look back at the definition of level set?
okay, sir, defined only level hypersurface.
For
Levels.
hypersurface, yeah, that gradient condition is there, but I don't think
Hmm.
it is for the level set as well. Level set is just the set of points that are given, that are taking us to that level. That's what
Oh,
it means. So level set at 0 means the points that takes the function to 0.
okay, okay.
That is M intersection W is the level set of G at 0. And we have one more condition. And this function G is such that now dg will be a linear operator, linear map, and eventually that can be represented by a matrix. So that matrix will eventually have rank and kernel, rank and sorry, nullity. So the rank of this dgx, now dgx is a matrix, we can find its rank. This should be equal to n minus t for every x in M intersection W. We'll see that using this condition, we can show that the unit sphere, in fact, any ball is a manifold, is an n minus one dimensional manifold. Next condition is that for each point A in M, we can find an open set W in Rn with, of course, it contains the point A and a CK smooth function, smooth map H from U to Rn, where this U is an open set in Rd. It's an open set. And H is a bijection. If I take this to be, so instead of Rn, we can say that H is from U to M intersection W, and H is bijective. In fact, the inverse, furthermore, the rank of the function, the rank of, yeah, this is CK
Derivative of hx is d.
rank of dh at any point x, this should be equal to d. Now dh, h is a function from u which is a subset of Rd, to M intersection W, which is a subset of Rn. So DHX will again be a map
RD to
from
RN.
some subset of RD to some subset of to Rn. So eventually this DHX, this will be a matrix of order
N
n
cross
cross
D.
d. Yeah. Now if its rank is equal to d
Hmm.
for every x in U, and this H inverse, now since we are saying that H is bijective, if you're saying that it is bijective, then the dimension should be same, right? U and M intersection W. But M is
Hmm.
in Rn. They're saying
Hmm.
that no, H is not a linear map. That happens for linear map. And H inverse from M intersection W to U must be continuous as
Without being linear, function
well.
can be bijective
Yeah, I think
of different dimension.
isomorphism. Yeah, we can find bijection between interval and sphere.
Um,
I think we can do that. Because for linear case, it's clear isomorphism implies the dimension should be same. But I don't think for any smooth function that would be fine. I'll look for some example if I can find out. This H inverse must be continuous. So yeah, these are three equivalent definitions of the manifold. So the main idea is if you want to visualize, so manifolds are very good if you can visualize them. So basically, it's a structure that is locally something like Rn. So suppose, yeah, for example, if we have something like this, suppose this is 3D. For example, you can consider the neck pillow. If you have seen something like this, neck pillow. So if you take any point and you zoom it out, so eventually, the way we say the part of a curve is a straight line. So in this case, if we are able to make it something like a Euclidean space locally, in that case, we say that this is a manifold. So if you want to see some example where it is not, if where it is not becoming a manifold, for that you can look at some structure of this form. Suppose this is some set in some higher dimension. In this case, any point here, you can make it locally something like Rn. But if you see at this point here, if any neighborhood you take, you'll get some sharp edges, something like this. And in Euclidean space, we don't have such sharp edges. No? So the problem occurs at this point. Similarly, yeah, in case of some donut shape also, in this case, you have a hole. So the idea is to make some set similar to the Euclidean space so that if we want to work on abstract spaces, we can use the properties of Euclidean spaces because Euclidean spaces are very well worked upon. They can be easily, comparatively easier to visualize. Not that easy for higher dimension, but still better than the abstract spaces. So that's the idea of manifolds. Let's look at some examples.
Why that sharp point actually is not in Euclidean?
I'll tell you. Suppose in this, let suppose I made this structure. Now I want this point, some neighborhood around this point to behave as Euclidean space. So I zoom it out. I should be able to find some small neighborhood that works something as we can say that something like a sheet. So, say for example, the point here, this might be a curve, but when you zoom it, you can eventually make it some straight surface. For example, on the curves also, we know that if we zoom the part of a curve, it will eventually behave as a straight line. So this happens in R. For higher dimensions, we want this to be something like a sheet. So, but here, no matter how much you zoom it out, you'll get something upper cone, lower cone. But you can't make that a complete sheet. For example, Earth, you can open the spheres. You can open that and make it a sheet. But in this case, you are not able to do it. So that's why this sharp point is the problematic point. Otherwise, here we can zoom it out, and eventually this is some sheet. You can make it 2D or easy to visualize.
Um, Actually, any neighborhood of that point will not be homeomorphic to open
Yeah,
set in
that's
RDF.
the basic abstract definition, no? Yeah, it should be homeomorphic to some subset in of Euclidean space.
Hmm.
So it's not
When
a
we
graph
remove
of some
that
smooth function.
point,
If you remove that point,
then
then you'll
connected
have
components.
then you'll have a disconnected space. I think in disconnected space still it will form a manifold. The problem occurs at these sharp points.
Uh,
Because yeah, in disconnected spaces also, still locally you can do that. But then
mm,
also maybe you'll have to cut it something like this. Yeah, if you have two frustums, I think in that case you'll be able to do. In this case, you'll be able to find make it locally
mm,
Euclidean.
Actually, in RD, when we remove one point, then number of connected component will be not will be one, but if in here it will be greater than equal to two, I think.
Still, I don't think connectedness will be any issue.
Because
Even if
when
the because we are talking about locally, it should be Euclidean.
mm,
I don't think, but even after removing one point, I think still will have that sharp edge, no?
mm,
Okay, so let's look
mm,
at some examples how to use that above equations, above definitions, equal to definitions. Let M be the set of points x1, x2, xn in Rn such that this x1 minus a1 square, so on up to xn minus an square this is equal to r square for some fixed
A1, A2, AN.
or some fixed a, which is a1 a2 up to an in Rn and R positive. So this is just an open ball. No, sorry, it's a
Sphere.
sphere in Rn.
Mm,
So now we'll use the second definition. So we define it.
Hollow sphere it will be, no?
Sorry, hollow.
It will be
Yeah,
hollow.
yeah. We are taking just the boundary. let x naught belonging to M be arbitrary. So by the second definition, for any point in M, we should be able to find uh, an open set W and define a function, smooth function G on this open set W. Now x naught belonging to M be arbitrary. Clearly, we can find any open set containing this point x naught. Let W be any open set such that this x naught belongs to W. So basically, this is the sphere. This is some point x naught. This is our M and this is our W. Now we define G from W to R. So basically, we define G from W to R n minus D. So in our case, our D will be n minus 1. So this is n minus 1, which is nothing but just R. And we define this to be G x. Any point in W is just n coordinate vector. So we define it to be x1 minus a1 square and so on up to xn minus an square minus r square for every x equals to x1, x2, and so on up to xn in turn. Next, we need this G to be such that its level set at 0 is equal to M intersection W. So now let Y belongs to the set of all those points x and W such that Gx is equal to 0. That means suppose this y is y1, y2, yn. In that case, y1 minus a1 square, so and so on up to yn minus an square minus r square. This is equal to 0. This implies this y belongs to M. And since it was an element in W itself, so I can write it as intersection W. So this implies the level set x in W Gx equals to 0. This is a subset of M intersection W. Conversely, also you can see that also if y is some element in M intersection W, in that case Gy will be y1 minus a1 square and so on up to yn minus an square minus r square. This will be 0. That means y belongs to the level set of G at 0. Therefore, M intersection W, this is equal to level set of G at 0. Another condition, the last condition that we need is the rank of the matrix dgx should be n minus d. So in our case, it is d is n minus 1. So basically the rank should be n minus 1. So let's see what is dgx firstly. So our g was a function from W, which is a subset of Rn to R. So obviously its derivative dg at any point x will be defined on some subset of Rn to R. And this will be a linear map. Eventually it will be a matrix of order order 1 cross n. And dgx, this will be given by del g by del x1 and so on up to
Gradient
del
of
g
G.
by del x2. Yeah, gradient. So this will be just gradient of G at point X. We want its rank to be equal to 1. So when will the rank be 1?
Mm, when gradient is non-zero.
Non-zero. So the gradient should be non-zero on M intersection W. Now let's see what is happening at M intersection W. So basically del G by del X1, if you see, this is equal to 2x minus, sorry, X1 minus A1. In fact, del G by del Xi, this is equal to 2 times Xi minus Ai for every I 1, 2 to n. So this gives us the gradient of G at X. This is nothing but
Summation
2 times, not summation, it is a vector. So it is a vector x1
multiplied by
minus a1 and so on up to 2 times xn minus an. So this is a vector 2x minus 2a. So can it be 0? In
No,
M
it cannot
intersection
be
W?
zero when x is not equal to zero.
Yeah, x should not be equal
Because
to 0.
radius is strictly greater than zero, I think. So x
But
cannot be equal to a.
how? A is a point on M
Mm. A
and
is
x,
the center of that sphere, I
sorry,
think.
yes. A is here and A can never be equal to x. This is never 0 for every x in M intersection W, because M intersection W lies on the surface of the sphere and A is the center of that sphere. This implies the rank of dgx, this is equal to 1, which is equal to n minus 1. That's what we want now. Our rank should be, rank of dg should be n minus d.
N minus.
Therefore, by the second definition of the manifold, this M, basically the sphere in Rn, is a manifold. Therefore, M, which is the set of all those points x1, x2, and xn, such that x1 minus a1. Now, since this a and r positive or arbitrary, we can say that any ball, any sphere is a manifold. X2 minus a2 square. Yeah, it is easy when we can find such a G. The problem is to find that such G. Xn minus an square, this is equal to r square, is a manifold. 1 second. Okay, so I hope this example was fine. You were able to understand how we are using the definition. Okay.
Yes, ma'am.
So
But
did you look for, huh?
but when any arbitrary example was given, then how can we find that function? How we can approach to find that function,
That
whether
is
it is
the issue.
manifold or not?
That is an issue. Basically, you need to see the points and judge that whether the points are turning out to be some graph graph of some function. That's the main point. So, for example, in the next example, we have seen the set of points xy equals to 0. In that case, we were not able to find any smooth function. So eventually, in that case, we'll end up getting some multi-valued function.
Hmm. Egg
Yeah,
point
the
origin.
yeah. That's the problem. Otherwise, it's fine. The problem was only at origin. So eventually, you need to find that function. Yeah, if we see that mm, the set of points m, x, y in R2 such that x times y is equal to 0. Now, suppose this is a manifold. In that case, we can find a function f such that this m is the graph of that function. So if we look at the set of points, so this is basically the x-axis and the y-axis. So if we define function f from R to R, for any non-zero x, I define it to be 0. In that case, I don't have any problem. But the problem is at 0. X equals to 0. In that case, if we can find any function such that it is the graph of that function, in that case, the function must be multivalued and hence the problem. So,
Why we take fx to be 0, ma'am?
yeah, because we want this x-axis now or for x non-zero. The set of all these points x comma 0, this will also lie in the set M, na? The product here
Hmm.
is also 0. So we the this M is basically x axis union the y axis. So for any x
Hmm.
non-zero, if I define f of x is equal to 0, I can cover this x axis except for the point 0. The problem is at for x equals to 0. For x equals to 0, I am not able to find any function such that its graph gives us the set of these points. And hence, this can never form a manifold. Then, yeah, next we saw that product of two manifolds, the cross product, Cartesian product of two manifolds is again a manifold. So using that, we can see that a torus. Torus is nothing but S1 cross S1, where S1 is the unit circle in R2. This will eventually be a manifold. In fact, it's cross product n times will again. We can't even imagine how this will look. We can't visualize it, but still it will form a manifold.
Ma'am,
Hmm?
in above when the graph is x and y axis, so the
Yeah.
problem is when it intersect at origin. So when we take two graphs which are not straight lines, if they intersect in R square, will they form manifold? Or the same problem will
Uh,
happen at the point of intersection?
so you're saying if we can find two graphs, so you're looking at two functions,
Mm.
f1 and f2.
Yes.
Suppose f1 and f2 are two functions. Suppose they are from R to R, R
Mhm.
to R. And then suppose M1 is the graph of F1. So this is just the set of points x comma fx. X is in R. Then M2 is the set of points x comma f2x and x is in R. Next, you want to take union of M1 and M2.
Mhm.
And you want to see whether this will form a manifold
Manifold.
or not.
Oh.
I don't know. Maybe we should look at some specific functions because
If
for
they
the cross
intersect,
product case, for the cross product case, we are able to do na. If we are taking M1 cross M2, then to we can find in similar way the manifold. And you're saying that if their intersection is
non-empty, then
M1 into. So do you have some specific examples of F in your mind that we can start with? M1 intersection
mm,
M2 is non-empty.
the above example is a specific case of this, I think.
Above
But
example, what will we take F2? F1, suppose you defined f of x equals to 0 for all x.
mm, up
Because
to
you can't define at 0 now. At 0, I want all the values of y. But that's vague. That's kind of a nonsense for the case of functions. Because we can't
mm,
give a point uncountably many values.
yes.
I don't know. Maybe we can do this. It should depend on the function, how the function is defined.
Oh, okay, ma'am.
Okay, so did you look at other examples of these manifolds? If you had some specific doubts, or else I'll have to see them. So yeah, for the
Ma'am, there is a question in assignment 7.
hmm,
It says which of the following are manifolds? One of the
okay,
option is the set obtained by applying an orthogonal transformation rotation to a manifold.
okay, you're just
And it
rotating a manifold.
oh, hmm.
I think it should be because
It,
rotation
this
is
option is
itself a
right.
linear transformation. Rotation is itself a linear transformation. So suppose we had a manifold, so clearly we already had a ck smooth function. You can just you are just composing it with a translate with the translation map. So the composition
Hmm.
will eventually be the same, the ck function. So eventually I think that composition map will give you the function that we need.
Okay. Hmm.
Yeah, just the composition. So basically you are just lifting the shape whatever it was and putting it at some other point. That's the only thing. So it should be the manifold.
Yes, it was the right option.
Mhm. Yeah, you can use this composition fact because translation maps are linear, so they are ck smooth.
Hmm. The union
And an
of two
example,
planes in RQ
union of two planes,
in RQ.
and the planes are passing through origin or parallel, or what kind of planes?
Just it is given a union of two planes in RQ.
So yeah, suppose there are two planes such that both are passing through origin or both are passing through some points. In that case, it will be something like this. So I think the problem will occur at
Intersection
these
point.
intersection points. Yeah, because if you look at this will be some again sharp edge type of thing. And if there are two parallel planes, in that case, I think it will form a manifold. So if it is just said that two planes, so in that case you can find a contradiction. In such a case, that this will not form a manifold.
Hmm. But in parallel
Similarly,
case, how it become manifold?
parallel case again, if you look at any point, it will eventually the neighborhood will eventually be some Euclidean space. So you need to define a function. You can define a piecewise kind of function. It should be graph of some function. No? Okay, so yeah, I'll look at these exercise problems of manifolds. I'll have to see that. How much time? Okay, we have just 20 minutes. Okay, we can leave it now. So if you have any doubt, we can discuss now. Otherwise, yeah, we'll meet then next Sunday. So right now, this critical point theory is going on in the theory classes, no? manifolds is done, then we have critical point theory, then we have integration over the manifolds.
Yes.
So
The
do you want me
exercise
to
12.7.
12.7? Yeah, this one, this eventually turns out to be the same as above example. So if we see the parameterization, this is kind of parameterization. T is mapped to t cube mod t cube. So if I want to plot the graph of this function, so this will be, if we take x equals to t cube, in that case our y is mod t cube. So that means this is just mod x. So what I guessed maybe, yeah, so y should be equal to mod x. And we know that the graph corresponding to mod x is not a manifold. Again, it will have a sharp edge at x equals to 0. So that is why this will not form a manifold.
So most of the case, sharp is
Yeah, sharp
gets
edge is
contradiction.
a problem. Yeah, sharp edge is a problem. And sometimes, for example, in exercise 12.8 and 12.9, I think in this case, the derivative will turn out to be 0 in some point. That will eventually give us that this rank is not the same. I'll have to see the calculations of these problems, exercise 12. So did you try these 12.8 and 12.9?
No, I,
Okay.
I was confused in this problems.
Yeah, I think here some derivative issue will come. Yeah, for this exercise 12.7, I think this should work because eventually this is the same as graph of y equals to mod x. If we see it as a parameterization.
Mm. Cos2t, cos2t is
In this case, just look at its gradient. Its gradient will turn out to be 0 at some point, and in that case, that the rank of dg, the rank of dg will not turn out to be n minus d. There will be some issue related to this definition, and hence it will not form a manifold. Just look at its gradient and try to find the points where the function is, where the gradient is 0.
Mm. So the second definition is very
Yeah,
useful.
I think it is quite easy to use. What I felt, most of the problems. Yeah, while visualizing, the first one is good because eventually you want the points to be some graph of some ck smooth function. So if you have a picture, then and you want to visualize, you want it to be locally similar to the Euclidean space. So in that case, maybe first, but by if you want to go step by step, I think the second definition is more useful.
Okay.
Okay, then I'll also try this exercise 12.8, 12.9, and then we'll meet next Sunday. Then hopefully I'll do some problems related to integration over manifolds and further problems. Okay, then.
Okay. Okay, ma'am. Thank you.
Hmm.